We know that in two-space, lines can be represented using vector equations, parametric equations, scalar equations, or just a plain old equation in slope y-intercept form. But as you have come to understand in this course, things in the real world rarely happen in 2D, so we need to be able to work with lines in 3-space or 3 dimensions. A line in 3-space can be defined by a vector, a parametric, or what we call a symmetric equation, and that's what we're going to look at today. How can we take what we already know about lines in 2D space to create equations in 3D space? Now, it is worth pointing out that we can create a vector and a parametric equation for 3D lines, but not a scalar equation. In 3-space, a scalar equation defines something different. It actually defines what we call a plane. And a plane is a two-dimensional flat surface that extends infinitely in all directions. So let's take a look today to make connections between vector, parametric, and this idea of symmetric equations of lines in 3D. So just like in 2-space, a line in 3-space needs two things. We need to have a position vector or to a known point. So we need to have some point that's on the line that we can have a vector, the tip of a vector pointing to. We also need to know a direction vector. And remember, we talked in the last lesson about that direction vector really being equal to the slope of a line, and it will be multiplied in our vector equation by some scalar multiple t. Well, the good news is in 3 dimensions, or in 3-space, the vector equation looks exactly the same, except now we have 3 components. We have x, y, and z. We still have our position or point vector. Remember, that was r naught. Except now we have x naught, y naught, and z naught. And we also still have our direction or slope vector, which is m1, m2, m3, or the three coordinates of the direction. We're going to call them a, b, c, multiplied by some scalar multiple. The other way that we looked at representing these was as a parametric equation. And remember, that just breaks it down into its components. So if we separate it into our components, we have, for our x value, we have x naught plus a times t. For our y component, we have y naught plus b times our scalar multiple of t. Now for our z value, we have our z naught value of our point or position vector plus c times our scalar multiple. The third one that we're going to look at is called the symmetric equation. And the symmetric equation is derived from the parametric equations and solving for the t parameter in each of the components. This is not in your textbook, but I'd like you to see it as you will come across it again in future calculus courses. And the symmetric equation of a straight line in space has the form x minus x naught over a, y minus y naught over b, z minus z naught over c. And if we really wanted to know what all of these things were, the x naught, y naught, and z naught is just the coordinates of the point. So that's the coordinates of some point. So I'm going to try and write it so you can read it. Coordinates of a point on the line. Coordinates of the point on a line. And A, B, and C are the direction numbers from the slope. So A, B, and C are just the values from our direction or our slope. So these are the values of the direction vector. Now, one thing to make note of here, because now our values of the direction vector A, B, and C are on the bottom of these fractions, that A, B, and C cannot equal 0 because we can't divide by 0, right? We can't, it's undefined if we divide by 0. So let's do some examples. So let's start by determining all three equations, the vector equation, the parametric equation, those are the two we're most familiar with, and a symmetric equation of a line that passes through 2 points. And let's call these point A and point B. So point A is at 0, 0, negative 5. That's my x, y, and z. Remember, x, y, z. And point B is at negative 1, 4, negative 4. So in order for us to be able to put this into the vector equation, remember we need two things. So my vector equation, x, y, z, is equal to the position vector, one of the points, doesn't matter which one we choose, plus some scalar multiple of our direction vector, which will be our slope. So let's start by getting our direction vector. And we're going to get our direction vector by looking at the line segment or the vector AB. And remember, to get the values for AB, we're going to be subtracting tip to tail. So basically, it's our B values minus our A values to get our new points. So we have negative 1 minus 0 for our X value, 4 minus 0 for our Y value, and negative 4 minus negative 5 for our B value. That gives us our direction vector AB of negative 1, 4, and negative 4 minus negative 5 becomes negative 4 plus 5. That gives us a value of 1. So we have our direction vector. We also need a position vector, R naught, which can be either point on a line. So let's use point A. So let's put this all together. X, Y, Z, square brackets because it's a vector. That's telling me it's not just a point on the line, it's a vector, is equal to R naught, which is our position vector, which has its tip at 0, 0, negative 5, which is a known point on the line, plus a scalar multiple of the direction vector, which really is equal to the slope anywhere along that line. It's a straight line. It's going to have the same slope all the way along it. And we can define that as vector negative 1, 4, 1, which is what we just found right here. So there's our vector equation of the line. So now let's break that down into a parametric vector. And remember, a parametric vector just breaks the vector equation into its x, y, and z components. And we can write that. Sometimes you'll see it written like this. Sometimes you'll see it just as x, y, and z. So we have our x value is going to be our x naught value, which in this case is 0, so we don't need to include it, plus t times our value, our x value from our direction vector. So we end up with negative t. So x is equal to negative t. The y value is same thing, only this time we're going to take the y naught value plus t times our y value in our direction vector. So we end up with 0, which we're not going to write, plus 4t. For the last one for z, same thing. This time we do have a z naught value of negative 5, and that will be plus 1t or just plus t. So there's our parametric equation. Now here's our new one. So let's go ahead and let's think about our symmetric equation. And our symmetric equation is x minus x naught all over the a value. So this is A, B, C, all over the A value from the direction vector. That's equal to y minus y naught all over the B value from the direction vector. And that equals z minus z naught all over the C value from the direction vector. And remember, A, B, and C are just the values of our direction vector. So let's figure that out. So I have x minus x naught. Well, x naught is 0, so that's just x. And my a value is negative 1. So it's x over negative 1. Now we have y minus y naught. There's my y naught value, so it's y minus 0, so we end up with just y on the top. And my b value from my direction vector is 4, so we end up with y over 4. Z minus z naught. Now, we have z now, and now we actually do have a z naught value of negative 5. And so z minus negative 5 becomes plus 5. So we have z plus 5 all over the c value from our direction vector, which was 1. So here is all three forms of our equation. Let's do the same thing for 2 more points. I want you to pause the video and try it yourself, and then come back to see the solution. Okay, so hopefully you've had a chance now to give it a try. We're going to do the same thing. We're going to create all 3 equations, the vector, the parametric, and the symmetric. So first thing we're going to do is label these points A, B. And this time, instead of going A, B, let's go B, A. For our line segment. So this time we're going to go BA, and that means that will equal our direction vector, and that will be equal to, this time, A minus B, right? So this is A minus B, tail minus tip. So we have 1 minus 1. We have 0 minus 0. It doesn't really matter, I guess, for those first 2 points, what direction we went. And then we have 0 minus negative 1. So 0 minus negative 1. That one did matter. So that gives us a direction vector of 0, 0, and 1. Okay, so we've got our direction vector. Now we're just going to pick a point. Doesn't matter which one, let's pick point A. So let's put together our vector equation. You would have been equally right if you had have picked point B. So let's say we've picked point A. I'll show you both just in case. So we have x, y, z. Our resultant vector, x, y, z, is equal to one of my points, my position vector, which has its tip at the point 1, 0, 0, plus t times our slope values or our direction values, which is 1, 0, negative 1. If you chose to do point B, it would look exactly the same. X, Y, Z is equal to, this time, 1, 0, negative 1 plus t times 1, 0, negative 1. So those would be our 2 possibilities for our vector equation of a line. So now let's look at the parametric. And I'm just going to stick this time with using point A. So our parametric vector, we just break it down into its components. So our line here will be equal to x, y, z. X is equal to 1 plus 1 times our t value, so 1 plus t. Y is equal to 0 plus 0 times our t value, so in this case, y is just equal to 0. And z is equal to 0 plus t times negative 1. So it becomes times negative, 0 minus negative 1t. So that actually just becomes t. So there's our parametric equation. Now let's do that last step and let's do our symmetric equation. So we have x minus x naught. Well, x naught is just 1. So we have x minus 1 all over the a value of our direction vector. So x minus 1 all over 1. Now our y will be y minus our y naught value, which is 0. So that's just y all over. I've realized I've just made a mistake. I'm not going to go back and read you the whole thing, but I am just going to go back and fix it. I transposed my direction vector incorrectly. That should be 0. It's 0, 0, 1, not 1, 0, negative 1. So, because I'm looking at this and I'm like, wait a minute, this isn't matching my answer. So this would actually be Actually, let's erase this. I am just going to go back and we're going to talk about this one. Okay, that's okay. Mistakes prove that we're learning. Okay, so take 2 on this solution. So our parametric will be, still have the line is equal to x, y, and z. So now let's get it right. So we have our x value is x naught, which is 1, plus t times 0. So that's 0. There is no value of t. Y is equal to y naught, which is 0, times 0 times t. So that's just equal to 0. And z is going to be equal to z naught, which is 0, plus our t value, t times -1. So that would be negative t. Okay, so now let's go back now that we fixed that and let's do our symmetric. Okay, so now for our symmetric, here we go again. We have x minus x naught. Well, x naught was 1 all over our a value, which is 0. And we have y minus y naught. Well, y naught was 0, so we just end up with y also over 0. That's our b value from the direction vector. Now we have z minus z naught, and z naught was 0, so we just have z all over our value here, our z value, which is -1. So we can see then, remember I said that a, b, and c cannot be equal to 0 because we can't divide by 0. So if we end up with any of these 3 relationships with a 0 in the denominator, it means there is no symmetric equation. And we would simply say here, therefore, there is no symmetric equation. Hopefully you had a little bit better luck at getting that one done than I just did without making that little mistake. Okay, let's take a look at one last example. Are the following lines the same, parallel, or neither? So let's think about what this means. So if a line is parallel, the direction vector, the slope vector of one of the lines is a scalar multiple of the other. And then if they're the same, if the lines are parallel, then we're going to check to see if they share a common point. So let's work through that process. So we have a vector equation and we have our symmetric equation. So the first thing that we're going to do is we're going to determine the direction vectors for each line. So let's determine the direction vectors for each line. And we're going to call this line 1, and we're going to call this one line 2. Okay, so remember, I can read the direction vector right off of the vector equation because that's going to be the second part. So my direction vector number 1 is equal to 3, -6, 3. My direction vector for line 2, now remember the direction vector here, the ABC values, are the values in the denominator of the symmetric equation. So I have 2, -4, 2. I think we can see that these are scalar multiples of each other, but let's go ahead and prove it by reducing each of them to their lowest possible form, the same way that we would do if we had just a regular straight line and we had a slope of y over x. So I can reduce this one to 1, -2, 1, just by dividing 3 out of it. This one I can reduce as well to also 1, -2, 1, again, by pulling out a factor of 2. So we can see that my distance vector for line 1 is indeed equal to my distance vector for line 2, and that is equal to 1, negative 2, 1. So therefore, they are parallel. Now that we know that they're parallel, we need to check to see if they're the same. So does a point on one line also lie on the other line? So let's get our point. So our point from our symmetrical equation is going to be our values here, because remember we have x minus x naught. So here's x naught, here's y minus y naught, and here's z minus z naught. So our point then, our point from that will be 2, negative 2, 5, because remember this is x minus x naught, and this is y minus y naught. So this has to be negative 2. This one needs to be negative 2. And this is z minus z naught, so z must be positive 5. So now that I have a point, we're going to sub x equals 2, y equals negative 2, and z equals 5 into the parametric equation for line 1. And if our t values are the same for all three equations, the lines are the same. They're not just parallel, they're actually on top of each other. So we have, in our parametric equation, we have x equals 1 plus 3s. I guess it's s values this time, not t. So it's 1 plus 3 times our multiple. For y, we have y equals 0 plus negative 6 times s. So that becomes negative 6s. And for z, we have 3 plus 3 times s. So now let's sub in these values. Let's sub these in. So if x equals 2, 2 equals 1 plus 3s, we're just going to rearrange and solve. So this becomes 2 minus 1 becomes 1 equals 3s. So s is equal to 1/3. So that's our first multiple. Now let's do the same thing for y. If y is equal to negative 2, that equals negative 6s. So s is equal to negative 2 over negative 6. If I reduce that, I get positive 1/3. Okay, so our first two scalar multiples are the same. Let's try with the third. 5 equals 3 plus 3s. This becomes 5 minus 3, so that becomes 2 equals 3s. So s in this case equals 2/3. They are not all the same. Therefore, these two lines are not the same, but they are parallel. Okay, so I want you to go ahead in ED. So I didn't realize there was a mistake there too. I probably should have just redone this lesson right from the very beginning. In 3D, not 2D. Okay, so here are some questions from the textbook. I would recommend going through and doing as many of them as you need to feel confident with this material. If you have any questions about it, feel free to send me an email.